Uh, this example or this exercise is in fact to uh, make us aware that the classical induction argument, which says that if you have a property P that depends on n, then basically we check the first ones are true, and then we assume that Pn is true, and we prove that Pn plus 1 is true. This classical induction argument may sometimes not work, and this is the case with this beautiful sequence of natural numbers, the Fibonacci sequence. And by the way, one has to just go to the internet and do a search, basic search about Fibonacci sequence. This is a beautiful sequence which has many applications. So in any case, so here instead of using the classical induction argument that says that whenever you have a property that depends on n, okay, and we want to show that this Pn is true, okay, so what we are going to do is first check few Pn's are true, okay, and then instead of having Pn true implies Pn plus 1 is true, what we are going to do is assume that P of 1, for example, if we assume that we start at 1, otherwise if you start at 75, you assume that P75 is true. The first ones, P sub 2 all the way to P sub n are true, and prove that Pn plus 1 is true. So this is the advanced, there are different versions of this induction argument, but this is the advanced one instead of using the basic one. And the reason why we are doing this is simple. It's very simple, because if you look at the Fn, the nth element of the Fibonacci sequence, it is defined from the previous two and not from the previous one. If it were only defined from the previous one, then we hope to prove, I mean, we can use the classical induction arguments and be able to prove whatever they want us to prove about them, okay? So this is the reason why we're doing this. So first of all, another surprising fact is why 1 plus square root of 5 over 2 and 1 minus square root of 5 over 2, what we call the golden numbers, or the golden ratio numbers. So in any case, these two numbers, this will be discussed at the end. I will say something about it, though the problem does not discuss it here. In our case, it's more about an exercise on the induction argument. But I will say something. I will try to say something at the end of this solution, okay? So number one, we check that F1 and for F2, the formula is true. Okay, the formula is true. Okay, clearly F1 is equal to 1 over square root of 5 times 1 plus square root of 5 over 2 minus 1 minus square root of 5 over 2. So this is true, okay? So it's true for n equal 1. If we go for n equals 2, then keep in mind that 1 plus square root of 5 over 2, we can check, by the way, the following identities is equal to 1 plus square root of 5 squared over 4, which is equal to 6 plus 2 square root of 5 over 4, which is plus square root of 5 over 2 plus 1. This is something that is a simple exercise that the people can easily prove, as well as 1 minus square root of 5 over 2 squared is equal to 1 minus square root of 5 squared over 4 is equal to 6 minus 2 square root of 5 over 4 equals to 1 minus square root of 5 over 2 minus plus 1. Plus 1. Okay? So in other words, these two numbers, they satisfy this beautiful identity, which is x squared equals to x plus 1, where x is both the two numbers. Okay? So that's what it is. Now this is very interesting because it will help us a lot later on in the proof, but the so in any case, so if we go to f2, okay, so it's gonna be so again, what do we want to prove? We want to prove that it's equal to 1 plus square root of 5 over 2 squared 1 over square root of 5 minus 1 plus square root of 5 over 2 squared here. So this is the identity that we want to prove. And as we just showed, so this will be from above equal to 1 over square root of 5. And the plus 1 that you have right here with this plus 1 will cancel. And then you will have 1 plus square root of 5 over 2 minus 1 minus square root of 5 over 2. And that will give us there is a square root of 5 here, so it will be 2 square root of 5 over 2 square root of 5 is equal to 1. So basically that f2 is equal to 1, okay, as claimed. So we have proven what? The inequality of f1 and f2, and now we want to prove the following, which is assume that the formula is true for f1, f2, fk. So we have fk equals to 1 over square root of 5, 1 plus square root of 5 over 2 to the power k minus 1 minus square root of 5 over 2 to the power k. Okay, and this is true for k equal 1. Assume this, for k equals 2 all the way to n. Okay, and we need to prove, let us prove that, okay, fn plus 1 equals 1 over square root of 5, 1 plus square root of 5 over 2 to the power n plus 1 minus 1 minus square root of 5 over 2 to the power n plus 1. Okay, so this is where we are going to use the inequality we just mentioned, okay, which is basically this here, okay, which we just said is exactly this when x is equal to 1 plus square root of 5 over 2 or 1 minus square root of 5 over 2. So what do we know? Now we have to go back to the way fn plus 1 is defined, or the definition, the basic definition of the Fibonacci sequence. So we know that fn plus 1 is equal to fn plus fn minus 1. Okay, so as you can see, the one that we want to prove the identity for is defined from the previous two, and that's why we need to assume that for the previous two, the equality is valid. Okay, great. So this tells me what? That fn plus 1 from the induction assumption is equal to 1 over square root of 5 times Okay? 1 plus square root of 5 over 2 to the power n minus 1 minus square root of 5 over 2 to the power n, okay, plus 1 over square root of 5 time 1 plus square root of 5 over 2 to the power n minus 1 minus, okay, 1 minus square root of 5 over 2 to the power n minus 1 here. And now we placed a little bit of algebra, so this is 1 over square root of 5 times, and we have 1 plus square root of 5 over 2 to the power n plus 1 plus square root of 5 over 2 to the power n minus 1 minus 1 over square root of 5, 1 minus square root of 5 over 2 to the power n plus 1 minus square root of 5 over 2 to the power n minus 1. Okay? So, this gives me 1 over square root of 5. And then we factor out 1 plus square root of 5 over 2 to the power n minus 1. And then we get 1 plus square root of 5 over 2 plus 1. And here we get minus 1 over square root of 5. And then we take, of course, to the power n minus 1. And then we find 1 minus square root of 5 over 2 plus 1. And again, if we go back to the equality that we showed before, we know that this will be equal to 1 plus square root of 5 over 2 squared, and this one will be equal to 1 minus square root of 5 over 2 squared, which tells me that if n plus 1 equal 1 over square root of 5, 1 plus square root of 5 over 2, n minus 1, and now we have 1 plus square root of 5 over 2 squared. And the same goes for the other one, minus 1 over square root of 5 times 1 minus square root of 5 over 2, n minus 1, 1 minus square root of 5 over 2 squared. And if I put the stuff together, I will find that 1 over square root of 5, okay, 1 plus square root of 5 over 2 n plus 1 minus 1 minus square root of 5 over 2 n plus 1 here. In other words, the inequality is valid also for fn plus 1 by induction. And this is what we wanted to show here by induction. The formula is valid. The formula is true for n equals 1, 2, etc. So again, as I said, what is this 1 plus square root of 5 over 2 and 1 minus square root of 5 over 2 is coming from? And the idea is, if you go back to the remark, so let's put it as a remark. Okay, so we have basically a sequence xn, okay, such that xn plus 2 is equal to xn plus xn plus 1. Yeah, that's what we have here basically. And of course, if we assume that the first two numbers are equal to 1, then we have the Fibonacci sequence. But what I'm trying to say here is, when do we have a geometric sequence as a solution? Geometric sequence as solution. Okay? So if you put xn equals a times power of a number r, then very easy to check that in fact what you have, I'm assuming of course that a is not equal to 0, otherwise we have the 0 sequence, which is the trivial one and it's not interesting. So here you will find that in fact your R is a solution of this quadratic equation, which explains the two numbers. So once you have found these two roots, 1 plus square root of 5 over 2 and 1 minus square root of 5 over 2, then you can show then that is a basis that generates all the sequences that you see there. Depending on the first two, then it's easy to find is a linear combination of these two geometric sequences. So, but there is a lot more to be said about this sequence. As I said, for example, what happens when n is large, you can ignore the 1 minus square root of 5 over 2, and you have that number 1 plus square root of 5 over 2 that takes over. It's really beautiful. In other words, just quickly, uh, so another remark, okay, which is that if you take limit when n goes to infinity of fn plus 1 over fn, so it's easy to show that it's equal to the largest of the two, 1 plus square root of 5 over 2. It's really beautiful.